Excellent. We're ready to go. It's a great pleasure to welcome Veselin Filev to give today's seminar. He's going to tell us about backreacted D0, D4 backgrounds.
Well,
and thanks, Veselin. Veselin is an old friend and so needs very little introduction here. Thanks, Veselin. You can begin.
yeah, thanks. I was hoping that I could give this talk, in present, but it's not possible at the moment. Please interrupt me because, yeah, it's better. When I see it says Corfu 19 here, ignore that. It's not the same talk. Okay? There are a few slides from that talk. Anyway. Okay, so what I'm going to talk about is backreacted D0, D4 background. This is something that we start discussing with Denjo and Tuma back in 2015. In 2019, we had some progress when we met in Corfu. And now this is almost ready work. It's just that since we waited on it for more than a year, I want to put more before we put it out. But I'm going to tell you what it is about and why are we interested in the D0, D4 background. Now, I'm going to start with a brief introduction to the Adcft correspondence, which is the context in which, well, it's not the context of our technical computations today, but it's the motivation behind. And then I'm going to talk about the D0, D4 system as a lower dimensional version of the Adcft correspondence with flavors. And then I'm going to talk about the Berkooz-Douglas matrix model, which is essentially the field theory dual to the D0, D4 background. So what we're doing is we're constructing the gravity dual of the Berkooz-Douglas matrix model. And then I'm going to talk about the backreacted D0, D4 background, how we can obtain this very naturally from 11-dimensional supergravity. We'll uplift everything to 11 dimensions. This is inspired by work by Cherkis and Hashimoto about the D2, D6 system. So that's why at some point I will revisit that one. And the technique that we're going to use is this Garfinkel-Vachaspati construction to obtain the solution. And then we're going to have to use another additional trick, which is to smear partially some of the D-branes to obtain an easier solution and more tractable. So what is the Adcft correspondence? It's a correspondence between type 2b supergravity or string theory, actually. The original one involves supergravity, but really we imagine that here supergravity is low energy limit of string theory. And n equal 4 superactants. So it's a duality between type 2b string theory on ADS 5x5 background and n equal 4 superactants. And this duality is weak strong duality, which makes it useful. Now, as soon as Maldacena actually proposed this correspondence, this formula was proposed, which can allow you to extract quantitative information from the correspondence. And the idea is to consider the partition functions in both theories and to say that they're equivalent. On the left-hand side is the generating functional in the quantum field theory. On the right-hand side is the tree-level diagram of scattering of a scalar field in supergravity. Now, this correspondence, the n equal 4 super-Young-Mills, it's just Young-Mills theory. And this calligraphic n, it stands for the number of supersymmetries. So it's maximally symmetric 4-dimensional Young-Mills theory. And as such, it doesn't have fundamental flavors, scalar fermions. So it doesn't have flavors. So here, as you know, in QCD, the fermions are fundamental representation. But the main way we distinguish between what we're made out of and what mediates the interaction is the whether it transforms in the adjoint or in the fundamental group. And in this theory, there are no fields in the fundamental representation. So that's why to introduce fields in the fundamental representation, it was proposed by this gentleman in 2002. to Karchin cuts to introduce D7 brain to the game. So the idea is that the D3, D7 brain system, if you look at it, if you write down the string theory that governs it, you can motivate, you can look at the field spectrum, you can see the supersymmetry of the system, and supersymmetry itself will fix the functional form of the field theory that you can write, the low energy effective field theory. And it's actually n equal 4 super-Young mules coupled to n equal 2 hypermultiplet. So this is completely fixed by, you don't need to do, it's completely fixed by supersymmetry and more, of course, but. And so now you know that the dual, well, not the dual, but the theory that describes the low energy physics of the D3, D7 system is n equal 4 super-Young mules coupled to n equal 2 hypermultiplet, which is fundamental. And the way it works is you imagine, I mean, I know that there are students in the audience, that's why I apologize if I explain things that are obvious to everyone, but still. So the thing is, the way it works is we imagine that the end of the strings are kind of like the quarks. That's how originally string theory was motivated, right, by Susskind. And now we say, well, the joint representation is just a cross product, fundamental and anti-fundamental, and the strings have orientation. And we can assign to one orientation fundamental, to the other anti-fundamental. And so if we have an open string ending on the same brane, we say, well, this represents a joint field because it has one fundamental and one anti-fundamental. On the other hand, if you look at strings stretched between the D3 and D7 branes, they have only one end on the D3 brane, and this would correspond to fundamental field. Now, what happens to the other field is the D7 branes are more dimensional. So what I didn't say is that when you write this theory, the theories actually live in different dimensions. And there is an extra component in the theory. Okay, there is the n equal 4 super-Young mules, which lives in 4 dimensions. There is the term that couples the n equal 4 super-Young mules to the hypermultiplet. So what I said is correct, it lives in 4 dimensions, but there is a Young-Mills theory that lives in 8 dimensions. And these are strings that begin and end with D7 brane that are not on this picture. The reason why they are not in this picture is because when you do dimensional reduction, you actually freeze them. This is, in this brain engineering techniques, if you wrap a brain on a cycle, the Young-Mills coupling is modified by the volume of this cycle. And here, because the D7 branes are infinite, you freeze these degrees of freedom. So the lower, so dimensional reduction essentially makes these fields here global fields. So they transform in the global group. So all the fields that transform this part of the representation, it's fundamental representation, but it's fundamental representation of the global symmetry. So it's a flavor symmetry. And that's why this is actually a way of introducing flavors to the game. And in this way, it is more similar to QCD. It's not the same, of course, but it's more similar. Okay. This is the way we study this in the context of this is just what I said with so we have the 3-3 strings that gives us the n equal 4 super-Young mules. 3-7 give you fundamental, 7-3 gives you anti-fundamental, and you have the 7-7 fields that give you gauge field that live on the D7 brane word volume. These are frozen when you reduce to 4 dimensions. Now, and so it becomes global symmetry. Now, the way you study this in the context of Adcft is you imagine that that's one way, of course, not the only way. You imagine that the D3 branes, if you place many of them on top of each other, they backreact and they form the D3 brane geometry. And if you go to the near horizon limit, you obtain Adcft crosses 5 space. Adcft crosses 5 space is near horizon limit of the D3 brane geometry, or it's the extremal P brane three brane geometry. Now, when you take that limit, if you bring the D7 branes closer and closer, as you take the limit, you're gonna end up with D7 branes probing Adcft crosses 5, and that's the idea. So the idea is, the proposal is you consider Dirac-Born-Infield action, which describes the probe D7 branes in ADS5 cross S5 spacetime. And the physics, whatever you get, should be dual to flavored N=4 super Young-Mills. But there is a caveat here, and this is the probe approximation. So it's only allowed if you don't backreact on the background. And that corresponds to so-called quenched approximation in the field theory. We have to be careful. It's not necessarily the quenched approximation, because NF much smaller than NC. It's not necessarily quenched, but it is pretty much quenched. So in this approximation, the only diagrams that are first order in NF over NC survive. Now, and the way the correspondence works is that the shape of the D7 branes, so when you solve the Dirac-Born-Infield action, that would give you some minimal surfaces in some sense, a bit more complicated than that. They describe this dual system. And the gauge fields that live on the D7 brane, you could use them to excite different external fields in the dual theory, like magnetic field, electric field, chemical potential, etc. And this has been studied a lot. Now, what we wanted to do some years ago was to test that on a computer. Why did we want to test that on a computer? It's a philosophical question, but we wanted to do it. And so the idea is, how can you do it? Well, there is a group that I know that often visits DIAS, by the way, that tries to simulate the N=4 super Young-Mills on the lattice. I don't know how successful they are these days, but they rely on a very special lattice construction, which preserves a lot of finite symmetry. And they argue that this kills a lot of the counter terms that are possible. Why is that important? Because if you put the theory on a lattice, it undergoes, when you take the continuous limit, it undergoes field renormalization, like it undergoes RG flow. And then you need this counter term, but you need to balance the counter terms numerically, which is impossible. And this is, that's why you can't always realize the naive continuous limit of the Lagrangian when you put the theory on the lattice. And so even if the Lagrangian seems to restore supersymmetry, if you put supersymmetric theory on the lattice, you won't get supersymmetric theory in the continuous limit. What these people argue is that they kill a lot of this blah blah counter terms, so that's why they can. But the moment we introduce the D7 branes, we break the structure, and also it was also very difficult to do. On the other hand, there is a parallel line, which is to study lower dimensional versions of the correspondence. In this case, one reduces the D3 branes to D0 branes by T-duality, and the reduction of the N=4 super Young-Mills to one dimension is in fact the BFSS matrix model. And so the BFSS matrix model is due to the D0 brane background. And this has been studied by many groups like Hanada and some of the people, sorry, yeah. And I don't have the names written here. And so we decided, well, let's consider a lower dimensional version of the D3-D7 system. Well, the D3-D7 system is T-dual to D0-D4 system. And that's why we said, well, let's study the D0-D4 system. But that is known already. Berkus and Douglas, they constructed such matrix model. Their motivation was the fact that BFSS model is related to M theory. And so they said, well, when we introduce some M5 brane density, we will have that would correspond to this model. The idea is that M5 branes in one dimension reduced to, from 11 dimensions, they reduced to 10 dimensions as D4 branes, and the membranes give you, well, it's that component is not so clean, but that's why this corresponds to D0-D4 system. And that we can actually simulate. So the Berkus Douglas matrix model, we simulated it with Yuma and Denju in 2015. And Sam also joined, and we had some nice results. That's it. I'm not gonna talk more about these results, except I'm gonna show you the Berkus Douglas matrix model, which looks like that. And it can be obtained if you look at the D5, D9 system. You write down the write down the action, and then you reduce to one dimension. And then this is, let's say, this is a 6-dimensional version of the Lagrangian. What it means is that all these spinors here are represented as 6-dimensional spinors. Now, okay, this is how it looks like. You could try and see why to integrate out the we could integrate out the adjoint fields, some of the adjoint fields, and here this is what this is meant to motivate, which is not very important for today's talk, is that in fact even in the quenched approximation you do get quantum effects from flavors. So it's not that you can simply kill the flavors in your determinant. The determinant is still alive, and strictly speaking, from a lattice gauge point of view, the theory is not quenched. So what you're restricted to is one fundamental loop. Here this dashed line represents fundamental loop. But even though you're in the fundamental loop, you still have expansion in terms of different loops. All right. So this tells you that the simulation should be done in such a way that the flavors are not quenched. Why was that important? Because we had already a code that was simulating the BFSS model. And we were hoping we could just leverage on that code to simulate the Berkus-Douglas matrix model. But instead, we needed to write a new code that simulates the Berkus-Douglas matrix model. And so what we did, without wanting, was to actually consider the full dynamical system of the D3D, of the D0, D4 system. But this is, then we numerically increase the number of colors to get to the proper approximation. And this was good, it worked okay. But we said, can't we just construct the actual background that corresponds to the unquenched limit, which is the backreacted D0, D4 background? And this is what we did in what I'm going to talk next. So we went back to the original system of D0 and D4 branes. And we said, instead of taking the D0 background and put the D4 branes as probes, why don't we backreact the whole thing? So how can this be done? Both the D0 and the D4 branes can be uplifted to 11 dimensions, and the D0 brane becomes a KK. Well, it becomes KK momentum. As we're going to see, by the way, it looks a little bit like a plane wave. Now, the D4 brane, on the other hand, I mentioned that already, uplifts to M5 brane. And so in 11 dimensions, this would result to constructing an M5 brane background with momentum. And this momentum, by the way, is along the M-theory cycle here, circle. So this is what we want to do. Now, this was not original thought. It was based by inspired, that's a better word. It was inspired by Berkus, by Cherkis and Hashimoto's work on the D6 backreacted system. And I'm gonna, by the way, spend at least 10-15 minutes talking about this system. Now, so Cherkis is the same Sergei Cherkis that was at Trinity. So they uplifted the M5, M2 membrane. The D2 becomes M2 membrane. And the D6 brane is, by the way, magnetically dual to the D0 brane. And these, the D2 and D6 brane, they're KK branes. So they, when you lift them in 11 dimensions, they do not correspond to membranes. They correspond to some geometry with angular momentum. In this case, it is Taub-Knot geometry. So, so it is known that the D6 brane uplifts to 11-dimensional background, which in the transfer space has Taub-Knot geometry. And what they did was they said, well, let me then take the M2 branes geometry and put in the transfer space Taub-Knot. That's all. Then this should correspond to backreacted D2, D6 when you reduce to 10 dimensions. And of course, you can check that afterwards by writing down Einstein equations, or you could write down the variations of the gravitino as usual and solve the BPS equations and see that supersymmetry will also be consistent with this background that they did. Now what we're going to use is this Garfinkel-Vachaspati construction, which was it was developed obviously by these people, but it was used by Rangamani to try and construct a plane wave background or something like that. So the idea is that it allows you to deform geometries. It's a solution generating technique. We're going to see how it works. But the motivation is still the same. I mean, we're going to uplift the M5 brane into 11 dimensions, and we're going to use this technique to excite D0 branes in some sense in this geometry. Now, how is this technique working? Well, it applies for actions of this form, which are, you know, the type 2b and type 2a. If you ignore some fields, theories are of this form, but the 11-dimensional supergravity is definitely of this form. So it applies for fields of actions of this form, and it states that it relies on the existence of hypersurface orthogonal killing field. So what this means, it's a killing field, which is that. It should be null, which is that. And the hypersurface orthogonal requirement is this here. And S here is any function. So if you have that function S, if you have a killing field, killing vector essentially, that satisfies this for some function S, then you can write a deformation of the original background like that. And the claim is that if this is the old metric, then this is the new metric. And this field satisfies harmonic equation here. It also satisfies this, of course, but this is what. So this is very simple.
And the point is that if you satisfy these equations, you are guaranteed to satisfy the Einstein equations.
Yes, it's a solution generating technique, provided the Einstein equations are derived from action of this form. So if your Einstein equations are derived from actions of this form, and in one solution there is a killing, well, there is a hypersurface orthogonal killing field. I might have skipped null here, maybe null hypersurface orthogonal killing field. And if you have that, which is this mathematically, then this is a solution generating technique. So this saves you some, you know.
Sorry, will you explain how the undeformed metric is? Will you say something about the undeformed metric?
The undeformed metric should just be a solution to the Einstein equations.
Okay, you're not going to go into that for the
No, I'm going to go into that. No.
And I won't interrupt. Okay, all right.
No. Please interrupt, because I feel, I mean, yeah, interrupt. The thing is, it is a solution generating technique which allows you to deform an existing solution into a new solution. The requirement here for, I guess, this solution is only that it admits such field, right? So if this metric admits such field for whatever action S, for whatever not action S, this is just unfortunate, you know, notation for whatever function S. So this S and this S are not related. This is for the benefit of the students. Okay, so now, as long as you have that, then this deformation, this new metric is guaranteed to be a solution. And furthermore, you could put here any function psi that satisfies this. Now, in what we're going to do is S is going to be trivial, S is going to be 0. And this is going to be trivially satisfied. And we're going to focus on that. So let's see how this works. Now, let's consider, so we will use first the GI construction to obtain the uplift of the D0 brane geometry. So the first exercise is you start with flat space in 11 dimensions. This is just flat space in 11 dimensions, nothing else. It satisfies Einstein equations. And then in this, I mean, in this flat space, there are obviously many killing fields, right? And then you look at one. Well, first you go to light cone. So you go to light cone coordinates and you arrive at this space-time. And now you say, well, I would consider this field. How about it? Well, you can see that it's null. You can see that it satisfies the other equations. You can check with S equals 0. And if just for historical reasons, replace psi with H, we learned that the deformation of the flat space to obtain the new solution is just that. Because this killing field written in coordinates is that, right? So this is just the psi km. This is just this, right? This is just this piece. S is 0, this disappears, and k mu is delta x11 mu. And you can check that it satisfies the commutator of that is 0. So for S equals 0, that you can check also. Now, well, that you could trivially kind of ensure by considering psi that does not depend on x11 in this case. And then you're done. And if you write this, then you obtain this metric. You just add this, you have that metric, and the only thing that you did was you added this piece to it. Now you massage this a little bit, and this is essentially the uplift of the D0 brane geometry that you can check. This is the usual ansatz for reducing. This source is here, the dilaton, and this would, if you go through the usual construction, this is how the uplift of a D0 brane geometry works. So it's very easy. You start with a solution, you do that deformation, you obtain D0 brane. Well, then we say, how about we start with M5 brane geometry? We do the same transformation, and we end up with, you know, the uplift of the D0 D4. It's as simple as that. And well, let's do it. So this is how the M5 brane geometry looks like. This is 6-dimensional flat space-time. And this is where the M5 branes are extended. And this is the transverse. Well, did I say this 6? Yeah, that's correct. And this is a transverse 5-dimensional space. It's 5 dimensions transverse to the M5 branes. Okay, and these are the warp factors. They don't look like the usual -1/2 in type 2 and type 2b supergravity, but in 11 dimensions, they're normal factors. They look like that. And now we focus on this part of the geometry, which is flat. Well, conformally flat, I should say, right? There is a warp factor in front, but this is here is conformally flat, and then nothing depends on Tx11. So we just do light cone transformation. We end up with that part. Then we say, okay, how about checking if that satisfies the GA requirements? It does, clearly. You do the transformation. You arrive at that. And that's it. This is the background that we need. So this is the background that is 11-dimensional uplift of the D0, D4 system. Now, there is a -1 here that occurred. This is again for historical reasons. It's optional, and it's just translation of X11. That's why X11 everywhere had the, well, okay, it didn't have that. it had it here, right? The tilde, this is the different x11, let me put it that way. So if you just translate x11 to be equal to x11 minus t, or yeah, you're gonna get this. Good. And you know, you have symmetry along the empty circle, which is x11, so you can translate as much as you wish with no harm done. All right, and this is the 10-dimensional reduction of the metric. By using the standard rules of dimensional reduction, you generate the dilaton. This here, this is essentially Kaluza-Klein reduction. This is the Kaluza-Klein field that would give you the Ramon-Ramon charge of the D0 brane. And the Ramon-Ramon charge of the M5 brane, well, this came from the charge of, of the D4 brane. It came from the, not Ramon-Ramon, but it came from the 3 form of 11-dimensional supergravity, which magnetically sources the M5 branes. So there is a, like, if you look at the 11-dimensional super symmetry algebra, this allows some central charges, and there is a 3 form living there, right? Like all these forms, they can come from supersymmetry. And I know people in the audience have derived these things, right? So, anyway, or I suspect. Okay. Now, so notice something. We know we have that, and then we should have the harmonic equation, that equation for H. And this is in the flat space. So in this case, in our case, this should satisfy harmonic equation for written in the D4 brane background, or in the M5 brane background. So if you write this down, essentially this is harmonic equation where the metric for the Laplacian that you use is the M5 brane metric, the undeformed metric. Now, and what you get is that this simple equation is not fixed by supersymmetry. It doesn't arrive from supersymmetry. It arrives from Einstein equations, essentially, right? That's why we use solution generating techniques. So now, when I say we, I'm slightly exaggerating. What we actually did was we did the supersymmetry stuff, the full stuff with the BPS equations. Then we derived that equation using conservation of angular momentum or Einstein equations. And then we realized that it could be done so easily with that solution generating technique. So that's why we're so confident that it works, right? Because we did the full stuff, and then we know that this works.
There are delta function sources, aren't there?
Hello?
There are delta function sources which give the
Hello?
charges. Hello?
Okay, I froze.
Is there a broadband problem? Hello, is anyone there?
Yeah, I can hear you fine.
Okay, I'm just wondering. I think it's Veselin's that's frozen. Okay, hi Veselin. Yeah. Okay.
For some reason, my connection froze, even though internet was fine. Let me start again.
These things happen, Veselin. That's okay. Yeah?
Yeah, they tend to happen to me. Anyway, okay. So
I'm just wondering, are there There are delta function sources, aren't there, for these equations?
Yes, yes. So this is a standard.
Yeah, just
Michael Duff, if I'm not mistaken. Was he Michael Duff? You know this guy, Duff, that was one of the Schrodinger fellows was working with him.
yes, he was. Yeah.
Okay, okay. So he this old stuff from the 90s. Yeah, I get to say old stuff for the 90s, right? Yeah, and in fact, there you can show that you can start with exactly what you want. You put delta function sources the way you would put them to source the Ramon forms. And then you could derive the full story and you would end up with, bottom line is there are delta functions, yes. But for only some of them. For the magnetic ones, there aren't. So part of them have delta functions, the others don't have.
Exactly. That's more or less almost the meaning of the magnetic ones.
Yes. Okay. Right. And so it's, yeah, that's true. But we didn't derive it that way, right? We derived it from Einstein. So now we have to, yeah. Okay. Anyways, let's go. Bottom line, there are. Now, here what I wanted to just mention is that instead of doing this, you could write down the D3, the super. You could write down the most general solution that preserve supersymmetry, like that breaks just a quarter of the supersymmetry, and looks like. Yeah, it will fix your ansatz, and the harmonic, the warping function you can fix by either using the Einstein equations, or if you don't like this, you could just construct the angular momentum associated to rotations along x11, and you could along x11, and you could write down that the conservation of this angular momentum is in fact equivalent to that equation. You could derive it that way. That's how we did. That's how we did it in 2019. Okay, that's what we did, or maybe earlier. I don't remember anymore. In 11 dimensions, and it will also give you that same equation. So there are at least 3 different ways to arrive at this. You could start with the supersymmetry algebra in 10 dimensions and use Einstein equations. You could start with supersymmetry algebra in, and use charge conservation. You could start with, for the D0 branes, you could start with 10-dimensional, 11-dimensional supergravity, and then use angular momentum or Einstein equations. I think you can always use Einstein equations. Or you could use these generating techniques. Now, so what I wanted to say next is that unfortunately this doesn't have a solution, analytic solution. And it has even more problems than that. Now, if you start expanding this perturbatively, it has very nice solutions. And you can show that at infinity, the leading component, you can fix only the leading component in the expansion at infinity if you impose asymptotic flatness at infinity. In this case, it's not asymptotic flatness. In this case, the intuition is that as V increases, you separate from the D4 branes or M5 branes. And because of that, this function H, which actually describes, it's sourced by the D0 brane charge. It will it will acquire the form that it has in flat space, or it will asymptote to the D0 brane background. That's the, but this doesn't fix your solution. This is not sufficient to fix your solution at all. So your asymptotics at infinity cannot fix your solution. And that's a problem. And that's what we are going to address now. And we're going to see how this was done. It is because, like, if you're thinking why is that, that's because you're not imposing Dirichlet condition at infinity. You're imposing only leading component. The subleading components at infinity are the ones that remain unfixed by the asymptotics. Okay. So this is, you cannot solve this background just by using information at infinity. You have to use some information in the infrared. And in fact, there are many backgrounds that you can construct like that, not just one. It's harmonic equation. But let's say you want to use the most symmetric one. Okay. Any questions about that? Am I frozen again?
No, you're not. No, you're working fine, Veselin.
Ah, okay, okay. I actually, I know what I can do. I see your pictures and they're not moving. Maybe I can just minimize them. Not pictures, your video. It probably is heavy on the, although my connection, I just did speed test.
No, it's been working fine at the moment. Just
okay, you just don't have any questions. That's nice.
I was asking questions, but
Ah,
others may have questions. So I think it's clear for the moment.
well, it was actually puzzling me because I don't know if you know this, but I am now mathematician on paper.
Yes, I noticed, yes.
So I talked to the people from various math departments there, and no one was actually that helpful. Not that they don't know. I just probably didn't talk to the right people. But at least for me, it was. I had problems with this because I know that, for example, when you have a black hole, fixing the symmetry and the asymptotics fixes the solution, right? And so,
Yes.
so why is it that I couldn't do it here? And it's because I'm not imposing spherical symmetry, I guess, right? And usually what you have in mind is you fix angular momentum, then if you fix angular momentum and asymptotic, you're going to fix the Kerr solution, right? And what I'm missing here is the analog of this angular momentum because I'm deforming the geometry. And now it's not an angular momentum, but it's something else. But there should still be, and there is actually even more that is missing here, and it's going to become clear, I hope. I'm going to speed up. I talked slowly because I was afraid I'm going to finish too early and look like I didn't prepare enough, but now I have to speed up.
There's no rush, Veselin, no rush.
No. Oh, yeah, I forgot there is no rush. That's good. Now, so we said, well, why don't we again get inspired by something that worked and see how it worked? And actually, to me, that's the nice thing when you don't fully understand things, you can find small miracles there where it's obvious for the really smart guys. Okay, so let's see. Let's see this small miracle. Now, well, let's look at the D2, D6 system that I mentioned. This is Cherkis-Hashimoto solution, and this is the D2, D6 system. By the way, when I arrived first in Dublin, I went to Cherkis, and I told him, let's do numerical D3, D7 system. Let's do this, let's do that. Well, he wasn't that interested. But even back then, I always wanted to do backreacted D something else numerically. So this is what we did actually. Now, so and why you understand now why he wasn't interested, because this is a very special case. So let's look at the Cherkis-Hashimoto solution, the D2, D6 system. Now. Right now, I can motivate why this is a special case. D6 branes are 7-dimensional objects. In 10-dimensional space, the transfer space is 3-dimensional. So in this transfer space, in which you actually look at this extended object as points, you actually have 4-dimensional space. And harmonic equations in 4 dimensions is Coulomb potential, and Coulomb potential is special. And because of that, that's the only case where you can actually get analytic solution. And that's why Cherkis was not interested, because there are people who are not interested in. It's much cleaner if you can get things analytically, right? Now, so if you do the analog of what we did, or if you just look at the harmonic equation for that guy in the rest of the metric, so which is that, or in fact in the full, doesn't matter really. You're going to write this, you arrive at this equation. Now, And this 1 over r, in fact, is where the Coulomb potential is. But it has another problem, that solution. If you try and do perturbative expansion in large R, it's very difficult. The solutions there are very obscure. Ours is very easy, right? So you gain something, but you lose something. So this perturbative intuition here, what happens at infinity, it's not so clean. I know because I tried, right? But it's just more difficult. But because of that, you get analytic solution. And the analytic solution, the way you do it is, well, this here is just flat space. So you do Fourier transform along this flat space. You essentially use Fourier transform along the R4. This is the R4 that is now just one. When I said 3-dimensional space, I didn't say space-time, right? But I was actually sloppy. It is 4-dimensional space. Okay, it's 4-dimensional. Now, wait a minute. It's not 4-dimensional. Well, it's 4-dimensional. Just a second.
Why is it 3-dimensional?
No. Sorry. This is the space that is extended along the. This is this space. This is this space. Okay. Yeah. This is the space in between. This is the transfer space, which is the 3-dimensional space. Okay. This is where the D2-branes live, and this is what splits essentially the D6 branes. This is the part that is extended along the D6 branes and orthogonal to the D2 branes. Okay, so this is what Y is. All right, and this is 4-dimensional because the D2 branes are 3-dimensional objects. D6 branes are 7-dimensional. 7 minus 3, 4. Excellent. Now you do Fourier transform. This is your equation, and that equation appears somewhere in the classical literature as Schrodinger equation, as you may expect with Coulomb potential, blah, blah. Now, it has a solution, and the solution is given in terms of the confluent geometric, hypergeometric function. This is the regular solution. It has also irregular solution. Okay, so this is it at infinity. And even for him, even for them, Cherkis and Hashimoto, at infinity, you could not fix the solution, right? Why? Because C is not just a constant. C is any function of P, any function of P. And when you put it through the Fourier transform back, it's going to drastically change your solution, right? And what they did was they said, well, we're going to fix this normalization factor. They used a very special property of the Taub-Knot geometry that when you look at the center of the Taub-Knot geometry, it becomes flat. Now, but not the full Taub, the Taub-Knot geometry with a radial coordinate. Now, and so what they did was this allowed them to fix the normalization constant to that. And this is that limit that I'm talking about. If you take that limit to this 10-dimensional background, or I think they did it in 11 dimensions, in the 11-dimensional background, you actually you get that, and now you require that HP of Z is such that when you Fourier transform it, you get the warp factor associated to M2 branes. That's it. So they had this M2 Taub-Knot geometry, and the Taub-Knot geometry, because it becomes flat in the infrared, this charge conservation in Berkus theorem fixes for you the solution locally to look just like the solution of M2 branes. We don't have that luxury, right? This is a very special thing they have here in the infrared that actually allowed them to fix that constant. And that sounded a bit discouraging, but then we decided, well, that's not how it happened, but it sounds nice. We said, can we recover this in another way? And let's see what this other way is. Can I recover Cherkis-Hashimoto's solution without using this luxury here, right? Without using this very special property of the Taub-Knot geometry. That in this limit, this thing will happen, right? This is m going to infinity limit, so it's a weird limit. Anyway. Okay. So what the authors used, as I said, is that the 11-dimensional uplift of the D6 branes is a magnetic monopole realized as tau knot geometry. And we don't have it in the D0 phase. So what we're going to do is we're going to use partial smearing. So we're going to separate the D2 and D6 branes. What I didn't mention is that this simple solution that I showed you actually corresponds to a solution when the D2 and D6 are sitting on top of each other. Now, so we're going to separate the D2 and D6 branes, and then we're going to smear the D6 branes in the space transfers to both the D2 and D6, which is this R3 that I mentioned. And this will actually create a real cavity, like a real ball inside this transfer space. And then I could use Berkus theorem to get the warp factor outside. And outside, it should be the same solution for the D6 brane warp factor as if I didn't have the cavity. That's how it's going to work. But the H, okay, so this is here how this is represented. You have the D2 branes, you separate the D6 branes, and then you smear them. This circle here represents a two-sphere, right? And then you have this cylinder, and you know the solution inside the cylinder, and you know the solution, in this case, also outside the cylinder. But the solution outside the cylinder wouldn't know. It will, well, it has two components. One is the warp factor of the D6 branes, the other is the warp factor of the D2 branes. The warp factor of the D6 branes wouldn't know that they were distributed. It will be a kind of like a Berkooz theorem here. It will apply, and with less words, this is the solution, okay, right? So it looks like the other one, except by continuity, when the warp factor reaches the cavity, I can fix the shape of the warp factor, and this here is still undetermined. So inside the cavity, this is the most general solution that I have, which is continuous, which corresponds to continuous metric at the cavity. Now, well, this is actually a flat, well, not flat space, but because these are constants now. Now the whole thing is that this is frozen. Like instead of this being a variable, it reaches some value at the cavity, and inside the value it remains constant, right? So it, yeah. And now I scale the coordinates, and what we obtain is this metric. So it looks just like a metric for a D2 brane in 10 dimensions. Now, the most symmetric solution here is the D2 brane geometry, and you get this solution. This is the relation between D2 and M2. This is standard thing. Now, when we go back to the original variables, and we require continuity at the cavity, I could do the Fourier transform of this term here, and I can do the Fourier transform of the other term, and I just require that when R is equal to R naught, I have this. Okay, it's just a relation. And this yeah, exactly. This, in fact, corresponds to, this is the Fourier transform that I obtained. Right. Now, next we consider, well, actually, sorry, I'm getting ahead of myself. All that we do here is we substitute back in the original variables and you do Fourier transform, nothing more. All right. These were scaled variables here, right? I absorb these factors. Now, all that I do is I absorb these factors to motivate that in this coordinate, it looks like just flat space with some D2 brane density. And then the most symmetric solution is the solution of the D2 brane. And then I restore, and then I write this. And here there is a modification of the charge of the D2 brane. But other than that, it just looks like a solution of a D2 brane. And then I restore the original variables. And here you can see the broken spherical symmetry. So instead of having R6, sorry, not R6, instead of having S7 symmetry, instead of having SO8 symmetry in this transverse 8-dimensional space. Am I doing this in 8 dimension? Let me make it right. In 7 dimensions, sorry. Instead of having SO7, you break down SO7 to SO4 and SO3. Okay, that's what is happened, and this is the factor that essentially breaks the symmetry, the spherical symmetry. This is the net effect of this shell, because that shell is not shell in, it's just shell in this part of the geometry, and it's not shell here. Right? So it's not fully spherical shell. It's just shell if you look in this part of the geometry. Now, and because of that, it breaks the symmetry. All right, and this is just R7 written in, broken into R4 cross R3. All right, so this is what you obtain as your Fourier transform. And now we impose continuity. Outside, the solution is just of the same form. Because it's the same equation of motion outside, the solution is just of the same form, but this is now a new constant. And this is constant depending on P. And now we say we impose continuity. So inside I have this, outside this, at the boundary, at the cavity, that should be valid. And this fixes my constant. So I get this constant. And this is my, so we just constructed a new geometry, which is the geometry of D2, D6 branes with partially smeared D6 branes. Nice. Then we take the limit, we say, because Cherkis-Hashimoto solution, they also consider the localized, but the one that we considered is the one where the D2 and D6 are on top of each other. If I shrink the shell to 0 size, it won't matter that they were on a shell. It would still be a point. So I should recover Cherkis-Hashimoto solution, and I do. I take BP, and notice I didn't use the luxury. Of course, it is present here because when I take this limit, I kind of like feel the interior of the Taubnat geometry, but I didn't explicitly use the property of the Taubnat geometry in the limit. So just by putting the shell wherever I want and imposing continuity at the shell, now when I shrink the shell, we recover the Cherkis-Hashimoto solution. So this was very important test because it shows you that this prescription works, right? Of course it should work, but this is a way of cheating and using your ignorance. Well, not exactly ignorance, but let's say lack of knowledge, which is the same, to construct the solution by putting a shell, and inside the shell the geometry, and then you shrink the shell. So this was very encouraging, and we decided to do it. So we go back now to the D0 D4 system. Again, we have the D0, and we separate the D4. We smear the D4, we obtain this shell. And now we say, let's look at what's the solution. Well, now, again, to obtain non-perturbative solution, you need to impose this boundary. And then we partially smear the D4 branes. This is, by the way, the warp factor of the D4 branes in this case. So it has the usual shape outside of the cavity. In the cavity, it's a constant, and the constant is fixed by continuity, right? So these two terms are, so this function is continuous. And now again, we don't use the Berkus theorem. I mean, we just solve the equations of motion. I just say it, but we don't really use it as, I mean, it follows. Now, so again, we define this factor K. And if we write down the solution, this definition of fields, the solution inside the geometry looks like this. And so again, it is something like a D0 brane geometry, right? With a modified charge and modified dilaton, but that's all. There was modification of the dilaton in the previous one, we just didn't consider it. And now I follow the same prescription. I say, well, the most symmetric solution is then this, and everything would look like it would work nice, except it doesn't. So what we'll break down is that when you try to take the limit of v not going to 0, that limit will be singular. I know because I tried. Now, and what further complicate things is that you know the solution outside only numerically. I didn't even mention how you construct it, but you can see that you get something singular. And then I digged in the old literature. I get to say old, and again the same Duff. Duff has papers in which they show that if you put D0 branes inside D4 branes and you try to find localized solution, that's unstable. There is in fact some restriction. It relates on, it is a more general result. If you put a brane within a brane, and when the difference in dimensions is some number 4, and when the D-brane is below 2-dimensional, this is unstable. So not only the D0 but also the D1. Okay, I'm not claiming this. I'm just recollecting this because I wasn't interested in this result that much, but I think it was something like that. The D0, D4 is definitely unstable. So what happens is that the D0 brane will dissolve inside the D4 brane. And that solution is known for quite a while. This is when you take the D0 brane and dissolve it inside the D4 brane as density. So effectively, then your charge is still 5-dimensional charge, 4-dimensional charge. So this is what will happen. If you put the D0 brane inside, so if you don't separate the D0 and the D4 brane, you cannot get localized solution. And this is what we see as this instability in the limit. But then why do we want to do it? I mean, why should we do it to begin with? And by the way, this could relate to things like there is some instability in the Berkooz-Douglas model. There are some flat directions of the BFSS model that survive when you put flavors. So this instability could probably be addressed in the on the lattice, but it cannot, because on the lattice we know it's unstable there, right? The way we study it on the lattice, we put it at finite temperature. But here, finite temperature will regulate this. The finite temperature will create a horizon, and when you try to actually reach that horizon, V will be regulated. It won't go to 0. So that's why, and I didn't mention, but what we're really after we do this is to get the finite temperature solution. So this is not really a problem for us. We're not really interested in the 0 mass limit at 0 temperature. This is, you cannot simulate that on a computer anyway, and for a very good reason. There is instability there, flat directions. So then we settle for, we don't settle really. It's actually a very interesting result. No, I'm serious. I'm not. There is, if you actually do the D0 D4 system at finite mass, you can get the spectrum, and the spectrum is discrete. At 0 mass, the spectrum is continuous. So you could hope to extract some spectrum, for example, from this. So what we're going to do then is we're going to keep the radius of the shell V0 finite, and this actually corresponds to a mass, to a fundamental mass, bare mass, nothing else. So that's the difference from what we did with Cherkis and Hashimoto. Other than that, we do the Fourier transform. We get this solution, and you see here you don't get. This is a very innocently looking equation, and then this same people from it was in fact a mathematician, a theoretical physicist. He told me, but this has a solution, but it didn't. After I went to talk to him, it turned out there isn't. So that doesn't have analytic solution. Like, it looks very simple, but it doesn't. And so what you do is you could construct perturbative solutions at infinity. You could construct formally, a series of solutions, because this behaves very simply when you expand. It behaves very nicely. But what you cannot do when you do this perturbative expansion is, unless you use the shell, you cannot fix the conditions in the infrared. And that's why we use the shell. And you could match the shell. You could consider the shell also perturbative. And you can have a fully perturbative solution in which you're going to do perturbation in V4. V4, you can think of it as kind of like depending on the ratio of the D4 branes and the number of D4 branes and D0 branes. And because they have, and it would depend also on the Hoof coupling. So because it's a dimension for quantity, but this is what V4 is. And when V4 goes to 0, of course, this is you recover the probe limit. So the geometry is the same of the zero brane geometry. But so you can construct perturbative solution. In fact, you can construct it at any order. It has to go numerical beyond first order. But before that, you can do it. And by the way, when I said that it's analytic, the solution of Hashimoto, of Cherkis and Hashimoto, that wasn't strictly true. Like only the Fourier transform is analytic, you still have to do a numerical integral at the end. And so you can get it to that here with a perturbative solution. So this is a perturbative solution that you can expand. You essentially expand this at infinity like this. And as I told you, it's built within the structure of the equation that the leading term of the solution at infinity will have this asymptotics. Almost, right? With most natural choice of let's say of constants of integration will give you this nice asymptotic. So if you ignore this term, this is just the D0 brane geometry. But you do have this term, and you can do perturbative analysis for that term. You can, inside the cavity, you do know the full solution. So you could perturbatively expand it, and then you could match this, and that fixes your solution, okay? And this is the integral that I mentioned. So that's the only integral, but like for a person like me, this is almost analytic. I mean, I do lots of numerics, so it's almost analytic, but this is on the same footing as the Cherkis-Hashimoto solution. They also have integral like that. The inverse Fourier transform cannot be done. Okay, this is, but you can actually do the full, well, thank you, but I reverse things. This is a very new thing that I just did a few months ago, well, a month ago. Like now not because we couldn't, I just, never mind, why? What we really do is you take the solution at infinity and use some numerical techniques where you impose this asymptotics at infinity and you match it with shooting techniques in the infrared. So what you do is, because you know the solution in the infrared modulo a constant, then you shoot from the cavity, and then you find your solution by imposing regularity, by imposing this asymptotics. And by the way, the only regular solution has that asymptotics. So it's just sufficient to shoot from the shell numerically and impose regularity of the solution. And that you can do very accurately by having perturbative solution at infinity. So you don't have to numerically propagate all the way to infinity. You propagate just far enough, which far enough doesn't need to be that far. And then you have a perturbative like expansion, like Frobenius, I think expansion it was called. So you can have that expansion. And the coefficients of the expansion you can fit numerically. And this is very accurate thing to do, right? You actually can generate as many points as you wish, and then you just do a fitting. And in this way, you can get a very accurate numerical solution. So that's what we played with. And then we also have some work where we put D4 brane probes and we studied the spectrum and the effect of this on the spectrum. And that's the work that we did. Yeah, that's it. So thank you.
Okay, thank you very much, Veselin. Questions? Doors open to questions.
Yeah, two questions. One, a very technical one, which may just be semantics and a more interesting one. At the end, you said that you get some Frobenius expansion, but Frobenius, I know in the case of regular singularities, and your singularity did not seem to be regular.
Sorry, regular, I couldn't hear. Regular what? Sorry.
Regular singularity.
Regular. Yeah, okay. That's true. It's not Frobenius expansion.
Okay.
So that's why I said it, I think Frobenius, but it works the same way.
Okay, fine.
It's not, you're right, maybe. No, you're definitely right. I say maybe because I'm not sure that what I did before was also Frobenius expansion. Okay. but you actually construct perturbative solution, and I program a lot, so I actually automate this. It constructs it for me. So, but you can construct it to any order you wish. But there is a caveat here: you cannot actually, because beyond certain order, the inverse Fourier transform won't exist. So there are problems here. But you don't have to worry about these problems at the level of fixing the regularity of the solution. So there is a term regulating this, and so okay, it's not that the inverse doesn't exist; it's just that the order will be violated. Mm-hmm. They would rearrange. So definitely it's not Frobenius expansion. That's why I hesitated very good. I'm very sloppy with these notations. I should be more careful. I'm a mathematician now officially.
Yes. Well, but more interesting question. You said that the instability in the D0 and D4 case is related to some BFSS stuff. So once
yeah, okay. So this is really more like a speculation. So what do you mean? The way actually Duff and collaborators studied this instability was very similar to that. They did smear, I think, the internal brane, and then they got some equation, and they saw that equation has a singular limit, and they commented that it's unstable. So this was not done in full glory, where you look for quantum effects, things like that. But what we know from the BFSS model itself is that it has flat directions there, right? It has flat directions. And we do know that when we try to simulate this BFSS model, we cannot do it at zero temperature precisely because of the flat directions. And we have to regulate them in some way. And because I know that this should correspond to the Berkooz-Douglas matrix model, I'm just speculating that probably this instability of the D0, D4 system that was observed completely in supergravity by Duff corresponds in the dual theory to the flat directions that are there in the D0, D4, but I'm not sure. I'm not that sure. But you could probably try to regulate like this sphere that we introduce, you could put it in the dual theory too. Like that would correspond to taking the flavors and smearing them using the global symmetry. So use the global symmetry to rotate them, kind of like put them on a sphere. Mm-hmm. And you could do that, and you could probably try and match this instability. And I suspect that it will work exactly in the same way, because if any regulation that you do of the BFSS model, when you try to remove the regulating term, you become unstable precisely of the flat directions. There is critical slowing down that you see. And so that's why my intuition tells me that they're related, but we haven't done this. Correct me if I'm wrong, Andrew, but I think.
Yeah, you're correct. I mean, the instability is a quantum instability, and quantum corrections would correspond to 1/n corrections. So if you can take large enough number of D0 branes, you won't see the instability. It'll just correspond to flat directions, and it's associated with the supersymmetry and the cancellation of the 0-point energies in the supersymmetric situation. You have flat directions in the potential, and they're just not lifted because of the supersymmetry, and they do show up in the geometry, as you're saying, in the dual geometry. And the dual geometry corresponds to the n equals infinity limit, and where quantum corrections are removed.
In fact, Duff's thank you for that. In Duff's work is some years before Berkus and Douglas's work, and maybe if we dig in this literature, there might be some comments related to that. But this intuition that Andrew describes, I think you get it mostly from the simulations, right? Like coming from, or you don't?
You get it from the simulation, but it's also kind of, you can get it from the picture, the membrane picture.
Okay.
The BFSS is a quantized membrane, and you get these spikes in the membrane. They correspond to these. It's a very spiky membrane at the quantum level.
Okay.
But
that's the 11-dimensional picture,
yeah,
right?
if you kill if you kill the quantum corrections, you can see that you're killing those spikes. You're getting some sort of semi-classic work.
Maybe in the 11-dimensional picture, that would correspond to, what would that correspond to? You try to create Kaluza-Klein momentum inside the M5 branes. So, and what is then the mass there? Well, it's more obscure, but you could probably get it. It should be, it's where, yeah,
the way to lift them, Veselin, would be to put it in a PP wave background, because a PP wave background it's growing at infinity. So it lifts those flat directions as well.
No, I meant the like this observation that like all that I did with we thought about it in 10 dimensions. Well, I thought about it in 10 dimensions. Now this shell, and then you put that, but this has it could completely equivalently be done in 11 dimensions, and there you're gonna get some geometrical picture in which you're gonna have this kind of like a vortex or whatever, right? And then its center relative to where the M5 brane density sits is your analog of mass. The shell. What is the meaning of the shell essentially? Right? What is the geometric meaning of the shell? Like the shell is clear as meaning, but now it's very easy in the 10-dimensional picture because I know I have density outside and I have density outside and not density inside. It's really a cavity of charge. But now this charge in the it's the same. Sorry. It's the opposite. It's the D4 brane charge. So it's just density of charges. Ignore that comment. So that what tells you is that it's that when these charges reach kind of like the center of this vortex, you get instability.
But maybe, I'm not sure whether we answered Werner's question in the end.
Well, that was very interesting. And you know, Veselin, you're completely right about well, real interoperability and so on. If the thing is under perfect numerical control, then it's as good as if you have an analytic solution. Anyhow, people, when you handle problems, then you're interested in NP or not NP and things like that, and not in formulas that you can look up in books.
Well, what you can get from analytical solution is a lot, but I mean, if it doesn't exist, you have to do numerics data.
And anyhow, it's sort of an accident. Well, basically, the definition of analytic solution is what you have in books already. And then you can invent a new symbol if some mathematical object is complete.
Yeah, of course, that is the. But even like that, that's why that's like there is a numerics and numerics. If at the end your numerics is doing numerical integrals, you can exactly do what you said. But I mean, there is numerics that. Yeah, I am not sure you can always do that, right? But in this case, the perturbative solution is exactly in that category. This very well defined integral, I could just give it a letter, as you said. But the full numerical solution that we do with this fitting, it might be. I'm not a specialist. You might be, if you're clever enough, you might break it down to pieces that you can label. Maybe I don't. Yeah.
Okay, I think Graham had a question as well.
Sorry?
I think Graham Kells had a question.
No, I didn't.
By all means, Val, if you're rushing off.
No.
Sorry. Graham?
No, I didn't have a question.
Oh, your hand was up, was it? For some reason?
No, I just clapped. I was.
Oh, I see. I
congratulating Veselin for a nice goal.
All right. Okay.
Okay.
Thanks.
Oh, thank you, guys.
Are there other questions? Well, if not, I will. I can stop the recording, and we can.